Let's talk about JFK. For those of you unfamiliar, November 22nd, 1963, our president was assassinated by Lee Harvey Oswald, supposedly. Whatever conspiracy theories are out there, don't follow conspiracy theories. Follow what you know. Physics allows us to do a lot of understanding of what happened. If you ever see any documentaries on this tragic event, then you're going to find a lot of explanations using physics. It's really quite interesting. So let's get to it. In an alternate universe, the motorcade transporting the president is traveling down Main Street when Kennedy spots Oswald in a much taller book depository in Dallas, Texas. Kennedy immediately draws a crossbow at time t = 0, fires an arrow directly at Oswald. The air does not affect the arrow in any way. Oswald tries to dodge the arrow by jumping out of the window from rest at exactly t = 0. So Kennedy is launching an arrow in this direction, while at the top of this building you have, right here you have Lee Harvey Oswald, the would-be assassin, jumping out of the window to avoid the arrow. Let's see what happens. What are the components of the arrow's initial velocity? We have 65 meters per second, and we have no angle. Oh no, Mr. Scapatis, what are we going to do? All right, so we are given a hypotenuse, this angle, the adjacent angle, and the opposite side. Or excuse me, the hypotenuse, the adjacent side, and the opposite side. So that means we can find the angle. Pick one. So, ka, toa. I'm going to pick so. Remember, the equation is sine theta equals opposite over hypotenuse. And if I want to get theta all by itself, I'm going to take the inverse of the sine function. So I'm going to get theta equals the inverse of sine opposite over hypotenuse. And when I do that, I've already calculated it, I get 23 degrees-ish. So, our angle we have now figured out to be 23 degrees. What are the components of the arrow's initial velocity? We know we are going to have an x component and a y component acting independently of each other. So the x component, cosine, right? Magnitude, 65. Cosine, 23. That gave me 60 meters per second. My velocity in the y is going to be magnitude cosine. Sine, 23. That gave me 25. As a double check, you can plug these two numbers back into Pythagorean theorem to see if you get 65 as your answer. At what height above the launch point does the arrow reach the building? Alright, so we don't have time. We have the initial velocity. And let me clean up this picture here. We know there is gravity, so we know the arrow, once it's launched, is going to be taken over by gravity. So it's not going to follow that perfect straight line. It's going to have parabolic motion. Not quite like that, but I'm never going to be able to draw it nicely, but it's going to look something similar to that, or roughly that. Right? So it's going to have parabolic motion, where here is probably going to be its maximum height. So if that's going to be the maximum height, then we know the final velocity in the y. We can set that equal to 0. We have the initial velocity in the y. We're looking for the height. But we don't have time. We don't have time. So we'll use the no time equation. Solving for y, we have 0 squared equal minus what did I do to solve for y? Oh yes, that's what I did. I subtracted v naught y squared from each side, and then I divided by negative 2g from each side. So I get vf y squared minus v naught y squared divided by negative 2g, and that gave me y. This will be negative on the bottom, this will be negative on the top, so I'm going to get a final positive height. And whenever I do that, I get 0 minus 25 squared is 625, divided by 20 gave me 68.75 meters above the ground. So it's going to be 68 meters from here to there. That's not quite at the top. Nice try, Mr. President. All right, at what time does the arrow reach the plane of the building? Well, we have all of this y stuff. Let's keep it going in y. Do we have enough information for the good old v as a function of t? We do. We have this. We need time. So if we solve for time, we have vf y minus v naught y all over g. 0 minus all over negative g, because that's minus g. 0 minus 25, so we have negative 25 divided by negative 10 gives us positive 2.5 seconds. So after 2.5 seconds, the arrow hits the building at 68.75 meters above the ground. At what height above the launch point is Oswald when he reaches the arrow? No, I'm sorry. At what height above the launch point is Oswald when the arrow reaches the building? Okay. So now this is a free fall problem. He's got an initial velocity in the y of 0. He's being accelerated by gravity. The time we know is 2.5 seconds when the arrow will reach the building. And his initial height, if he's up 100 meters above the ground, is going to be 100 meters. All right, so let's see. I've got initial velocity g, t, and y. We're looking for the final height, so we'll use the displacement formula. And we have v naught y times t minus 1/2 gt squared. Initial velocity in the y is 0, so we're going to have final height equal to half of g, which is 5, times t squared, 2.5 squared, (6.25) times 5 gives us, he's fallen a height of 31.25 meters. He's fallen a height of 31.25 meters. That means from here to here is 31.25. So as he's going down,